that people often divide themselves into, at least 4 boxes in fisheries. There's people that are doing stock assessments that are, mandated since the 1950s and further back, to achieve on a continuing basis some maximum sustainable yield, concepts of sustainability at a population level. There's also people doing habitat assessments. So, trying to think through marine spatial planning or human impacts on a landscape. And I think this will grow in importance because a lot of times, if you care about communities, if you care about in Alaska about, localized impacts for Alaska Native communities or, individual ports, then you have to get into localized decision making at a finer scale than stock assessments typically done. And that's typically done in what I call habitat assessments. There's also integrated ecosystem assessments. There's, at least since the 90s, there's been a real policy push to provide ecosystem level information and come up with target and limit reference points and, management policies that can, seek better ecosystem status. And then, of course, there's also a huge and growing interest in climate assessments. How is, both for mitigation, restoration, and adaptation. So International Panel for Climate Change, multi-decadal forecasting for informing, mitigation scenarios, but also kind of downscaled adaptation studies, and increasingly like how do we restore, habitat in the face of climate impacts. So all of those end up with different, typically end up with different programs and divisions within NIMS or different journals, different teams of people working on them. And, my claim is that we want to be working towards an analytic framework that can encompass each of the types of inference. And I'll claim that can be done using these spatiotemporal models, these models that seek to estimate, numerical density or biomass density at individual locations, indexed by space and time across multiple variables. And the benefits of that single approach is that you can, as an ecologist, we often think about ecological mechanisms occurring at fine scales. We can improve communication by showing kind of maps. There's nothing more intuitive than a map to most people. And we could also have similar review standards. There's sort of ongoing disagreements about which of these are more or less rigorous. And I hope that we can resolve those disagreements by having similar review standards. So as one of just, kind of an arbitrary plot that I pulled out a long time ago, a multivariate spatiotemporal model seeks to make predictions, in this case of numerical or biomass density of different species in a community across space and over time. So this is just cutting out 6 panels of a much larger panel figure showing 87, 88, 95, 96, 99, 2000 for each of 4 groundfish species caught in a bottom trawl survey off the Northeast US, the Northwest Atlantic. And, these types of maps, I think, are fairly interesting and intuitive by themselves. So in this case, silver hake, for some reason, from the 80s to the 2000s, seems to have increased in the Gulf of Maine. You can immediately see that Atlantic cod around the same time and in Georgia's Bank went from abundant in the late 80s to pretty sparse by 2000. You can see this sort of habitat, average habitat utilization, which species are kind of Gulf of Maine versus Mid-Atlantic versus Georgia's Bank. And so, these are types of information that any ecologist will know about their species, but are not really communicated within stock assessments, where we try to reduce everything down to a single time series. And, basically the software does this by defining an extrapolation area in latitude and longitude. So defining in this specific plot, defining a grid of an extrapolation grid, I call it, in latitude, longitude, projecting that using, in this case, a UTM projection, but it could be any geographical projection. And then it predicts densities across that landscape by tracking densities internally at a series of knots, KNOTS knots. And then it interpolates or extrapolates from knots to all of these extrapolation grid locations. That's what's happening internally. I do have these slides for equations, and for some people this will be useful in a literal way. Other people, for better or worse, get nervous about equations. I don't think anybody should be, but for those that this doesn't help them gain intuition, bear with me, I guess. So in the top here is sort of a short explanation of that the software that we'll be using, VAST, can fit to biomass sampling data. So, a measurement of biomass at a given place and time for a given species. And it does that using what's called a delta model. And so that delta model tracks encounter probability R1 and expected biomass R2. Alternatively, it could fit to count data. And in that case, it fits a zero inflated model in which 1 minus R1 is a zero inflation probability, and R2 is the expectation of non-zero parts of a count. So it's either a zero inflated model or a biomass sampling model, and both of them, in both cases, there's two components, something related to encounter probability and something related to density. And each of those has a bunch of different components that affect it. So each of those is modeled using a linear predictor. And in this context, I'll call that linear predictor P for, P1 is affecting R1 and P2 is affecting R2. And this will be visible in the software later. So I want to hit the kind of large concept. So each of these linear predictors has a component explaining temporal variation. So it's indexed by category and time. Each of them has a spatial component, omega, that's indexed by space and category. And then a spatiotemporal component that's indexed by space, time, and category. And category could be multiple species, it could be multiple ages, it could be multiple types of measurement for a given age and species. But category is the multivariate part of this model. S is for space and T is for time. It also includes optionally vessel effects, habitat covariates, catchability covariates, and fishing impacts. And we can talk about that later. But the core part of it, as might be obvious by it being called a spatial temporal model, is that it decomposes variation in, say, density into a temporal component, a spatial component, and a spatiotemporal component. And it specifically does that using these sort of factor model decompositions. And so that's what's shown at the bottom for this temporal component. So if you're going to learn a second word here, it's a factor model. Let's see, I thought I put in, it's fine. So can people see a mouse here? Is there any way to access a mouse? Does anyone know?
We can see a mouse.
And let's see, here we go. Okay. So this L is a loadings matrix, and I'll show that in detail later. And in this case, beta 1 TF is the value of a factor that then is expanded across all the different categories in the model. So there's a loadings matrix L, there's a set of parameters beta. That's sort of the key part. And you can estimate an autocorrelated structure across time if you choose to. Similarly, this is the same linear predictor in each of these slides, and I'm just kind of changing what's at the bottom. There's a spatial variation component that has a loadings matrix again that expands from the number of factors that are included to the number of species. And that spatial variation essentially follows a multivariate normal distribution across space that's then projected, interpolated using a matrix A, which if that doesn't, again, that probably won't sink in for anybody until they see it later. but there's a loadings matrix across species for a given spatial term. And then similarly, the spatiotemporal variation, by the fourth unit, I'm hoping that people will have a better intuition for what this means, has two loadings matrices, one of which expands from the number of factors to the number of hypothetical categories like species, and another loadings matrix that expands across time, which we will see later is useful for detecting sort of regional modes of variability. So those are sort of the key parts of the model are the temporal variation, the spatial variation, and the spatiotemporal variation. And those typically involve a loadings matrix, or optionally involve a loadings matrix that that I'll talk more about later. So then another kind of key decision is that we've defined these sort of two linear predictors, P1 and P2, and we then translate those to R1 and R2 that were used to fit the data. And you can either do that using this sort of logit and log link function, like in a generalized linear model. It's the same meaning about a link function. Or there's this optional Poisson link delta model that I've written about before. And so again, you don't need to follow the equations here in any detail, but I think it's worth kind of pointing out that word bank. Yeah, so I think given that we've spent about 15 minutes, I'm just going to switch over to code, or resources online, and then we can talk more about covariates if we have time in this first half hour. Does anybody have a quick question before I switch over?
I don't see any in the chat, but there's been a lot of back and forth for me. So if you wrote a question in the chat and I somehow missed it, please send it again.
Great. And that's fine. My training with these virtual, seminars or workshops is to just give a lot of chances for people to ask questions. So bear with me. Okay, so that's sort of the overview. Maybe I won't share yet. The overview, the kind of key take-home messages that I want people to think about is that there's a need to have a model that predicts density or other variables across space, across time, and across species. And if you do that, you could do habitat, stock assessment, climate, or ecosystem inference. And then in this specific R package, VAST, it decomposes that variation into a spatial component, a temporal component, and a spatiotemporal component. And the software will end up being different ways of specifying those types of variation. So going back to sharing my screen and going to the agenda, you saw the slides. There's a background and kind of a background reading that reviews this if people are interested in details. I have never bothered to put any of this up in CRAN, but there's a bunch of resources here that are listed on the GitHub wiki. So this GitHub is a a version tracking software that's online. This is the landings page for VAST, and then of course the URL it goes to this part of the landings page that lists 11 different resources for learning about more details. So I think what I wanted to point out was the reference documentation. So and I've got a bunch of versions of R open with different examples, which I will ignore for now. So in R, let's see. I always forget what the hotkey is for zooming in here. So technically, I'm using a version of R in Windows called Revolution Open R that additionally loads this MKL library to speed up linear algebra. It's not necessary to do anything that we're going to do, but you know, on my laptop, I've got 8 cores, and so it speeds up models about 8-fold. You know, I'm assuming most people have kind of vanilla R, and things will run a little bit slower on their machines. So here I've loaded R vast using this library vast call. And then I'm actually not sure if I've set up all, you know, updated all this stuff recently. Yeah, so, you know, at standard to R, if you just type question and then the package name, you should get sort of a, I call this the reference documentation, and I write it using something called Doxygen. And so sometimes I mistakenly call it Doxygen documentation. But, you know, here's some of the uses for the model. And in the details, you can see some kind of cross, you know, linking to, you know, via hypertext. So fit model, you know, is sort of one of the 3 workhorse functions. The 3 functions that we'll see over and over again today are probably listed down here. Yeah, exactly. So the wrapper functions, as I sometimes call them, are fit model, make settings, and plot results. And so we're looking here at one of the 3 kind of workhorse functions or high-level user interface functions. And it has a bunch of inputs that we will interact with more later. I just want to point out for now that there is kind of reference documentation with a description of each of these inputs like you'd expect in any R package. The other, let's see, from the agenda, I think the other thing I wanted to highlight was what I call the user manual. I mean, these days I call it I sometimes call it the user manual, but I mean, technically it's sort of you know, a Word document that has all of, you know, a detailed description of the model structure. So unlike the reference documentation that's more oriented towards the user interface, this kind of model structure or user interface document is really designed to kind of review the mathematical details. So for instance, here, there, you know, line 65 of that user manual talks about the linear predictor and says some of the same stuff I just said. You know, it just talks about temporal variation and has the second line I showed. And so, you know, for anybody who is interested in learning more about the details of what I just kind of skimmed through, you know, verbally, I was just trying to give people kind of a word bank of some of the concepts. But the user manual is where, you know, I document in detail the model structure decisions. So I think that that was all I really wanted to hit with this first half hour. Of course, I could dig into more details, but first I'll tab back here and do another kind of call for questions. Like, does anybody have any other type of ways of interacting with software that they, you know, besides that reference documentation and besides that user manual that they're especially interested in seeing where it lives? Okay. Well, maybe I'll spend the extra time then going back to the list of resources. You know, so everybody learns differently. In that agenda, I linked to this 2019 paper where I provide sort of like a decision tree for different user decisions. And so, for instance, in this paper, I don't know, let's see, it's probably not open access, so maybe this isn't super helpful, but I'll just point out that decision tree while maybe sharing my UW affiliate professor password. I don't know.
I can throw it in the shared folder on Drive if that's useful.
Oh, that's a good idea. Yeah. Yeah. So for instance, this paper has what's intended to be sort of a decision tree. And some of these concepts we'll understand better in a minute. But like, for instance, if you have multiple categories, first you kind of have to define the spatial domain, how many categories you have, what types of data, whether you have variation over time. And then, you can kind of play out sort of, do you want to put in covariates? What kind of link function and distribution do you want? Or alternatively, if you have spatial variation, you put in spatial or spatial temporal smoothers, the number of factors, and then finally a set of decisions about derived quantities that we will talk about more in a bit. So anyway, this is sort of where we go for, kind of a high level decision tree. There's also, oh yeah, of course, the what will be work. Let's see, that a dead link. There is this wiki here. So if you go to the kind of vast main page and then click on this wiki icon at the top, on the right-hand side is this sidebar that lists 12 different sort of example applications that are packaged with, have data packaged with the code. And, in this 4-hour chunk, we'll be going through 3 of these examples, 3 of these 12 in detail. But, people could note that there's, a feature for stream network models or surplus production models or seasonal models and so on. And then there's sort of a series of usage demos about how to plot in ggplot, how to simulate new data, and so on. So that wiki has a lot of the kind of core documentation more in kind of example format. And maybe I'll just pull out a couple more of these. There's an issue tracker where people are invited to submit issues. There's a listserv where a couple times a year I send out a summary. There's a news.pdf document, kind of standard to R packages, where anytime I make a new numeric release, I summarize what was changed. And there's a publications list that I try to keep track of how people are using it. Let's see, just kind of going on with the PowerPoint. I said that there, people can use covariates. So the model structure so far, it has a linear predictor and it has some link function. And so this, for people who are familiar with it, that might kind of ring a bell, kind of sounding like a generalized linear model or a generalized additive model, like GLIM or a GAM. And similar to a GLIM or a GAM, you can include covariates as well. However, the model is different from kind of standard LM or GLIM or GAM software in R, in that it imposes a constraint that you always define sort of a spatial area at the beginning of the analysis. And it does that so that you can distinguish variables that affect catchability from variables that affect density. So in a linear model or a GLIM, you only have a choice of whether to include a covariate. And then after you fit the model, if you extrapolate your model to new areas, you have to decide whether to include a given variable when you're predicting or not. And that's that implicit decision is specifying whether, when you fit it a GLIM or GAM, whether a variable is treated as affecting catchability or density. And in VAST, by contrast, it has an explicit distinction between a catchability covariate and a density covariate. And so, for instance, a catchability covariate is something that an attribute of a sample that affects the outcome of sampling, but doesn't represent variation in what you're trying to measure. And so, for instance, like people might have, I often deal with a semi-pelagic species called pollock, where people sample it with a bottom trawl, but they also sample it with a paired midwater and acoustic design. And so, you might think about trying to combine data from these two different gears, and that could be a catchability covariate, or it could result in a more complicated kind of vertically integrated model structure that I won't discuss in any detail. There's a lot of species that forage closer to the surface, a lot of fish that forage closer to the surface, following the kind of DL vertical migration of zooplankton. And so time of day, like whether you sample during the day or night or dusk dawn, oftentimes affects catch rates. Those are kind of classic catchability covariates. By contrast, there's other covariates that do, presumably, represent habitat quality. And so, including them is meant to represent variation in the density of what you're trying to measure. So something like prey availability or bathymetry might be a density covariate, whereas sampling gear might be a catchability covariate. And as I say here, some processes might affect both catchability and density, something like temperature. If you measure temperature in a given gear, that could be a proxy for habitat, suitable habitat, but it also might be that at lower temperatures, things are eating, have a lower metabolic demand and are less likely to pursue a baited hook. And so with something like temperature, it could be that it simultaneously is driving catchability and density. And so that's sort of a caution about covariates in general.
Sorry, Jim, are you interested in showing something? Slides?
Oh, that's so funny. Yeah, I switched back to the, thanks for pointing that out. I switched back to the PowerPoint.
Yeah, thanks to Sydney for
that. Yeah, I'm sure I'll keep making that mistake as I toggle back and forth between trying to look at faces and then trying to share. Yeah, so you can see my screen here. So I've been just kind of reading off, discussing this sort of covariate slide here, where I sort of summarize, some of what I just said. And then the last slide I provided for this section was kind of pointing out a little bit about the interface. So if you go to the reference documentation for fit model, you can see that there's sort of a, one thing called covariate data, X1 config CP, and X1 formula. And those, I'm also summarizing, let's see, summarizing here. So these X1 formula, X2 formula, Q1 and Q2 formula, these are kind of standard formula interface using LM or GLIM or GAM and R. And you could use splines or interactions. To use them, you also have to provide a data frame that's used as a lookup table when parsing those formulas. And then there's sort of a set of optional configurations that you can use to modify how it interprets those covariates that are called X1 config, X2 config, Q1 config, Q2 config. And so again, if you wonder about what those mean, you can look up the details in the reference documentation. So for instance, here it points out that a given item in this matrix X1 config allows you to turn off a covariate or have a linear effect, a spatially varying effect, or sort of a density dependent effect, which I've got a new paper sort of discussing. So again, that's not intended to be sort of like an exhaustive summary of any single concept, but the point is to kind of walk people through how, if they have a question, they could kind of toggle back and forth between the user manual that's online, the reference documentation where you can look up the interface, and then, you know, a series of papers where these concepts are discussed in more detail. So before going on, I'll just do another little pause here for any questions.
Is there a limit on how many covariates you can include?
Yeah, it's a good question. I mean, you know, there's a practical limit, kind of similar to LM and GLIM and GAM in terms of interpretability. You know, unlike LM, GLIM, and GAM, VAST runs kind of slower because it's computationally a more flexible platform. And so, you know, unlike in GLIM, GAM, you know, it's slower to do model selection. And so a lot of times if people have 100 covariates, they do backwards model selection to figure out which of the 20, you know, which of those matter. And it's much slower to do that in VAST. So that's sort of a practical constraint. You know, there's all the same caveats as with GLIM and GAM in terms of not using highly collinear covariates. And then, you know, just noting that, you know, time limits, I guess I'll point out that in the wiki, there is one of these that, let's see, I've got too many tabs open already. If you go to the wiki, there's sort of a section here about adding covariates and then visualizing covariate responses. So in this case, you know, I'm using like a basis spline. Let's see. Zoomed in a little bit. Hopefully that's helpful. So here I'm defining an X1 formula using this tilde notation and defining a basis spline for the log of depth, or a basis spline for log of depth plus a polynomial, a second order polynomial for bottom temperature, just kind of making up different covariate responses. And then I pass those along by passing this X1 formula, X2 formula, and covariate data. So people, you know, by the end of this, or even during the breakouts, should feel like they have enough background to run this code snippet. And then more recently, and somewhat probably more hopefully numerically stable, although it's a recent feature and I don't know that I have a whole lot of integrated testing, there's sort of two different ways of visualizing covariate responses, either a marginal effect or a partial dependence plot. So those are sort of concepts that come out of GLIMs and GAMs as well, and are different ways of visualizing the covariate response and the associated error and, you know, variance in that. Any other quick question before we switch gears to the other unit? And then we'll have a break.
Yeah, I've got a general question. Hopefully I'm not jumping the gun. So if VAST defines or kind of predicts densities based on a fixed spatial grid, is there a built-in way to like train the model on one spatial grid and then extrapolate that to a different spatial grid? Whether or not that's ecologically justifiable is a different question, but
it's a good question. The short answer is no, that you have to define the sort of geographic extent and resolution that you want at the runtime. And you know, there's sort of some pros and cons to that, as I'm sure you could imagine. You know, for instance, there's sort of a new set. I haven't done this in the software, but there's, you know, something we discussed that you know, there's a kind of new set of diagnostics for transferability. So like if you have measurements of covariates in a certain range and then you're predicting to a radically different set of covariates, you know, there's ways of modeling how transferable it's likely to be. And so again, unlike GLIM or GAM or a lot of other packages, it forces you to define this geographic extent and the covariates in it that are used both for prediction and for model fitting. And I hope in the future to kind of build in those sort of, you know, transferability calculations. again, that's a very different sort of structure than the way most functions are written in R. And there's sort of some intent for it, but it also constrains users, as you can imagine.